Jai Hind everyone. My name is Dr. Dibya Bharti. Today we are going to discuss subject Energy Science and Engineering. Subject code is KU033 or KU043. So today we will discuss topic electromagnetic energy. So in this subject we study about energy. So there are four universal kind of energy that exist around us, and one of them is the electromagnetic energy. So we get energy from sun, that is due to the electromagnetic radiation that all of us are knowing. So now we will discuss how this electromagnetic energy can be stored even, and it can be transmitted over a long range also. So this is the advantage of this energy. So that's why today we will discuss this. So first, what is the electromagnetic energy? So electromagnetic energy can be termed as electromagnetic radiation also. As I told you in previous slide, that electromagnetic sun is sending us energy. We are receiving energy from the sun due to the electromagnetic radiation phenomena. Okay, so this electromagnetic energy can be termed electromagnetic radiation also. So it is a common term that is being used to describe the energy associated with the electromagnetic waves. Okay, so as we know, when there is transmission of energy through the electromagnetic waves, so those are known as the electromagnetic radiation, and the energy that is being transmitted by through the electromagnetic waves, or the energy which can be explained on the basis of electromagnetic waves, those are the electromagnetic energy. So electromagnetic radiation has no charge or mass, and it moves in a pack of light energy or photons. Okay, so this electromagnetic radiation, it will not be having any kind of charge or mass, and it moves in a pack of light energy. Okay, so those are also known as photon. Okay, so electromagnetic energy is one of the most significant energy in the universe, and it is the entity that drives the electromagnetic waves. Okay, so as we discussed that there are four universal forces are there. Okay, and one of them is the electromagnetic energy. Okay, electromagnetic force. So it is the most significant energy in the universe, and it is the entity that drives the electromagnetic waves. So electromagnetic energy gets released when an external force accelerates an electric charge. Okay, so when we accelerate any electric charge through the external force, okay, so that force may be due to any reason. Okay, so but when we are able to accelerate the electric charge that is accumulated over any place, so when we are able to accelerate that charge from one place to other place, so that is called the release of electromagnetic energy. Okay, so basically we can say that when we are able to accelerate the electrical charge from one place to other place, or from one particle to other particle, that is called the movement of current. Okay, and that is also known as a release of electromagnetic energy. So these are the points that we can summarize from the previous discussion, from our discussion from slide 1, previous slide, that all solar energy that are being transmitted to earth, those are the electromagnetic wave. Okay, so that is the electromagnetic radiation, because from sun to earth the energy is being transmitted via the air particles, okay, in the form of light waves. Okay, so total yearly solar energy input is 1.74 into 10 to the power 17 watt. Okay, so that is the total yearly solar energy input to the earth. So primary solar energy consumption is there in the electrical power sector. So what we are doing nowadays, that we are harnessing the solar energy, and primary point of harness is to convert the solar energy into the electrical energy. Okay, that is the convenient mode, and that is the best mode to harness the energy from the sun. There are other applications of the solar energy also. We use the solar energy in the heating, in the pumping also. Okay, so that is the direct application of the solar energy. But solar energy, best thing is that solar energy can be converted into electrical energy, and then electrical energy as the secondary source, as we are knowing that electrical energy is the secondary source of energy. Okay, that is not the primary source. Okay, solar is the primary, but electrical energy is the secondary source. So because we cannot use directly solar energy, electrical energy. Okay, we use solar energy directly to convert that into the heat. Okay, to use the pumping. Okay, we used to we used to harness the solar energy for heating also. Okay, for pumping also, but we cannot use electrical energy directly. Okay, because suppose we are using the light, so that means we are converting the electrical energy into light energy. Okay, so we are rotating our fans through the electricity. Okay, so that means we are converting electrical energy into mechanical energy through the motor that is there in the fan. So we are not that's why electricity is the secondary source of energy. Okay, so but primary solar energy consumption is there in the electrical power sector. Okay, so as we are knowing that India is leading in the solar segment. So role of electromagnetic phenomena is energy flow, as we discussed in earlier slide, that when we are able to move the electrical charge or we are able to accelerate the electrical charge, that is the flow of electromagnetic energy. Okay, so role of electromagnetic phenomena is there in the energy flow. We are receiving the energy from sun to the earth, that is also the electromagnetic phenomena. So electricity generation is conversion from fuel, nuclear, those are the conventional, and when we are talking about the electricity generation from the solar energy, so that is the non-conventional source. So there are few formula that are used while we are transmitting the energy. Okay, so in case of radioactive and solar microwave, so this is the formula of the energy transmission, S equal to 1 by mu naught E into B. E is the electric field, B is the magnetic field. Okay, so for high voltage transmission line, when there will be transmission, there will be losses also. Okay, so when we are transmitting power, electrical power over a long range or medium range transmission wire, so loss can be written as I square into R. So now primarily we will discuss about the electromagnetic energy storage. Okay, so how they are being stored. So electromagnetic energy can be stored in the form of electrical field or magnetic field. Okay, so in the both form we can store electromagnetic energy. Okay, so the there are two ways. Primarily we are having two methods, two classifications are there for storing the electromagnetic energy. One is in the form of electric field and another is in the form of magnetic field. So when we store electromagnetic energy in the electric field form, so we use capacitor. Okay, and when we store electromagnetic energy in the form of magnetic field, we use the coil, inductor. Okay, so this is the basic principle behind this, because all we know that capacitor and inductors are the energy storing devices. Okay, those are the passive devices, but they store energy. Okay, so energy storage, as we know from our previous knowledge, that energy stored through the over the capacitor is half CV square. Okay, and energy stored over the inductor is half Li square. Okay, so these things will be discussed in detail also here in this today's top lecture. So practical electrical energy storage technology include two devices. One is EDLC, electrical double layer capacitors, EDLCs, or ultra capacitors. Those are also known as ultra capacitors, electrical double layered capacitors, EDLC, and SMES, superconducting magnetic energy storage. So first, as we know, when we will be using EDLC, that means that will store electromagnetic energy by the electric field, in the form of electric field. Okay, and when we will use superconducting magnetic energy storage, SMES, that will store energy in the form of magnetic field. So now we will discuss EDLC and SMES in detail. So electromagnetic energy storage, basically we know the energy density of an, if we talk first, we will discuss about the EDLCs. So as we know, the energy density of an ordinary capacitor is therefore determined by the permittivity. Okay, so as we know, so and the breakdown electric field and the dielectric material. As we know that the capacity of capacitor to store the energy, or we can say energy density, depends on the permittivity, okay, electric field that breakdown electric field strength of the capacitor and dielectric material that we will be using between the plates of the capacitor. So, electrical double layer capacitors differ from the ordinary capacitors by having an electrolyte between the electrodes, okay, instead of solid dielectric. Okay. So, how this differs? So, what we do, as we know that C, as we can write here formula. So, what is C? C equal to epsilon naught A by D. Okay, when we use the dielectric, we write the capacitor K also. Sorry, dielectric constant K also. Okay, so how we can increase, and we know that energy storage capacity of capacitor, energy stored over capacitor. Okay, so we can write this as, suppose EC, that means energy stored over capacitor, is half C V square. Okay, so simple concept is that we can as we increase capacitance, we can increase the energy storage over the capacitor. Okay, so and what are the methods for increasing the capacitance? Is that either we can increase the dielectric constant by changing the dielectric material, or we can increase the area, we can decrease this distance between the plates. Okay, and we can increase the permittivity also. So, these are the terms that are associated with the capacitance, and as we increase capacitance, energy stored over that will be increased. Okay, so but there are some limitations. We cannot increase the area between the plates. Okay, because that will give the charge leakage. Okay, there are charge positive and negative charges are there, those are accumulated over the plates of the capacitor, and we as we increase the area, the charges will be leaked. So, we cannot decrease the distance also, because for that, in that case also there will be leakage, there will be problem. So, there will not be flow of current. Okay, so what we do, best choice is to change the dielectric material. Okay, so EDLC differs from the ordinary capacitor in the way that in this EDLC, the dielectric between the plates of the capacitor, okay, so that is the electrolyte instead of the solid dielectric. Okay, so an EDLC consists of two electrodes with a porous separator between them. Okay, so that is the electrolyte. The separator is a polymer membrane that is approximately 100 micrometer thick, okay, which provides electrical insulation between the electrodes. It is pigmented with an electrolyte, okay, a liquid solvent in which a salt has been dissolved, and it will allow conduction of ions, but it will prevent the electronic conduction. Okay, so it will not allow the movement of as electrons are there, as we know there are holes also. Okay, so it will prevent that movement of the holes, it will only allow the movement of the electrons. So, double layer capacitors are also known as super capacitor or ultra capacitors, and due to their very high capacitance due to the other ordinary capacitor type. Okay, so as we discussed, so we can change the capacitance in other way also, but those methods are not preferable. As we increase the area, there will be problem of size. As we change the dielectric, as we change the distance, there will be problem of charge leakage. So, best way is to change the dielectric constant, and best way is that we will use the electrolyte between the plates of the capacitor, which will be porous kind of material. Okay, so polymer membrane of around 100 micrometer thick is being used for the EDLC. So, which increases the capacitance up to a marginal value. So, the electrodes and impregnated separators are rolled up and placed in a sealed container. I will show you the diagram also. So, when a voltage is applied over the electrodes, the corresponding electric field will cause ions of the electrolyte to move towards the electrode surface. Okay, so the surface consists of porous carbon which does not react with the ions, and ionic layers therefore form at the electrode surface. It results in an effective double layer of charges. Okay, so that's why it is also known as EDLC, electric double layer capacitor. Okay, so this is the concept that I had discussed, that general idea about changing the capacitance. Okay, so general idea of the conductor is that place a charge in on a conductor. So voltage on the conductor is proportional to the charge. Okay, so Q equal to C into V. Q equal to C into V. Okay, or V proportional to Q. Okay, so capacitance is the proportionality constant. Okay, so when we place a charge over a conductor, okay, so there will be we can see that the charge Q is proportional to the applied voltage. Okay, so that means V is proportional to Q, and if we remove this proportionality, we will have to put a constant. So that constant is the capacitance. Okay, so we can define the capacitance also. So capacitance can be defined as the capacity of conductor to store charge. Okay, so electric energy stored in the capacitor can be given as half CV square. Okay, so now parallel plate capacitors. Okay, we use two parallel plate. Okay, two parallel plates of area A that will be separated by a distance D. Okay, and suppose we feel a dielectric material over there, which is having the dielectric constant epsilon naught. So that is shown here in the diagram also. So this is the area of the this is the area. Okay, so this is the distance D, and in between this there is dielectric material that is placed, and dielectric constant is epsilon. Okay, so in here capacitance C can be written as epsilon A by D. Okay, so as we discussed earlier, so we can increase the capacitance by increasing the area. Okay, so by decreasing the distance. Okay, and by changing the material between the plates, so that value of the epsilon will be changing. So as we increase the capacitance by increasing area, there is limitation of size. As we decrease distance, there will be charge leakage problem. Or if we increase the dielectric constant, so materials are limited. Okay, all materials are not having the dielectric property. Okay, as we know. So so that's why all these three methods are having problem. So as we discussed in previous slide, what we had done, that we are using the electrolyte between the that is the porous membrane, okay, as the dielectric material. So special scale for capacitive. So there is so typical scale for the measurement of capacitance is farad. Farad is the SI unit, and typically we use picofarad and microfarad range of capacitors. Okay. So electrical energy storage can be done through the battery also. Okay, so at some place, best way is to place the battery in parallel with the supercapacitor or EDLC. Okay, so batteries are expensive. Okay, batteries are expensive, and those involve rarely and unusual material. Okay, so like suppose we are using the lithium ion battery. Okay, so lithium is a rare material that is not being found all over the world. Okay, so that is a problem with the batteries. So batteries are made with the relatively rare and unusual material. If we go for the good quality battery, like lithium ion battery are having the good quality, they are having the longer life, but material for that is the lithium, that is limited over the world. Okay, over the earth. So that's why this is the problem with the battery, and battery becomes expensive. Okay, apart from this, life of battery is also in comparison with supercapacitor, battery life is also very short if we see between supercapacitor and battery. Okay, so storing energy in capacitor, basically it is not a new idea, but using the novel kind of material that we are using in the EDLC, that is the new. Okay, so that's why in the smart grid also, if we go for the energy storage, suppose we are using the harnessing the energy with the solar and wind, there are numerous renewable energy sources are there. So in that case, we need energy storage. Okay, so preferable to battery, supercapacitor or ultra capacitors are being used. So super or ultra capacitors are made of this we had discussed that electrodes in the super or capacitor or ultra capacitor, electrodes electrolyte is there for the porous membrane. okay, that we discussed. 100 micrometer thick porous membrane will be there, but electrodes are made of graphite carbon in the form of activated conductive carbon or carbon gel. So electrodes are made of from the graphite carbon, okay. So separator will be there, as we discussed, porous membrane, okay. So that will allow only the electrons to flow, okay. So it will block the electronic current, okay. It will only allow the electrons to flow, okay. So this is the structure of the EDLC, we can say. So electrolytes are there, okay. So this is the porous membrane, okay, that is, and these are the electrodes. At these are the current collectors wall, and in between these two electrodes load will be connected. So if we compare ultra capacitor and conventional rechargeable battery, though that were used previous to the ultra capacitors for energy storage, electromagnetic storage, we see, I have taken here the rechargeable battery example, like nickel metal hydride battery was used because that was the rechargeable kind of battery. So now, since ultra capacitors are having very fast charge and discharge rate, okay. So if we see this comparison table, ultra capacitors can be charged and discharged at the rapid rate. They are having greater number of power cycle. That means they can store more energy, okay. So no environmental disposal issues are there with the ultra capacitors. When ultra capacitors are, suppose their lifespan has been elapsed, so if we dispose that ultra capacitor, because there is a porous membrane only, and that is the electrodes, those are made of the carbon, so they don't create any environmental harm. So also ultra capacitors are having very low internal resistance. That means in that, if resistance is high, that means there will be heating problem, okay, because at the resistance there will be drop, and that drop will be dissipated in the form of heat, okay. So but in case of ultra capacitors, there are very low internal resistance, so that means there will be low heating, okay. So if we see the specification, or if we see the properties of the nickel metal hydride battery, we see, so we are having the, in case of battery, we will having the low total energy is low. Intrinsically, it is a low voltage cell, and voltage drops linearly with the discharge, okay. Also, it is having the environmental problem also. When we dispose the battery, so they causes the environmental harm, okay. So some of the battery materials are there, they release the harmful gases while in use also, okay. So that's why manufacturing of some batteries has been stopped, because batteries are not environmentally safe, especially when we dispose them, okay. So leakage times, it is also having the leakage problem, okay. So it is low voltage cell, low energy. We can store energy over the battery, but if we compare the battery and the super capacitor, so energy storage capacity of ultra capacitor or super capacitors are much higher than that of the battery. So now, second type of energy storage material is the superconducting magnetic energy storage, SMES. In earlier first slide, we discussed that we store electromagnetic energy in two forms. One is in the form of electric field, another is in the form of magnetic field. So EDLC or ultra capacitors are energy storage device for in the form of electric field, okay. So in that we store energy in the form of electric field, and in case of SMES, we store electromagnetic energy in the form of magnetic field. So super SMES store energy in the form of magnetic field created by the flow of direct current through the superconducting coil. As we know, when there is flow of current, there will be magnetic field surrounding to that, okay. So their primary, what is the primary advantage of this kind of energy storage? So that the primary advantage of SMES compared to other energy storage is that there is short reaction time and ability to provide high power for short periods, okay. So that's why this SMES is also being used in parallel with the EDLC, because they can provide high energy in short time, okay. Because there is no time delay, okay. SMES system, suppose we know that the conductor, in case of capacitors, we cannot get the instant charges, we cannot get the instant flow of current through the capacitor. So because that is based on the charge accumulation concept, okay. So SMES system can counteract abrupt changes in demand for applications when even a shortest interruptions are unacceptable. Okay, so when there is a shortest interruption, suppose there is no power for microsecond also, that is not allowed in the real system. Okay, so that's why SMES systems are also SMES storage is also used in parallel with the EDLC. Okay, so because in real system this shortest, or you can say this negligible short span of time is not acceptable. Okay, so ignoring but problem is that in with the SMES system we have to put the cooling system. Okay, because we will see the diagram also. So ignoring cooling losses, if we ignore the cooling losses that is there, because cooling system will be associated with this SMES, and that cooling part is the loss. Okay, so if we ignore the cooling losses, they have the high round trip efficiency. Okay, so if we neglect the cooling part of this, then it is having the high efficiency. Okay, so typically 95% for higher for the superconducting coil itself. Okay, so 95% efficiency will be there with the SMES. So this gives SMES system an advantage for applications involving many charge discharge cycle. So what is the formula of the energy storage for the inductor? That is half Li square. So that is the concept. If there is current carrying coil, if coil is there, okay, over which current I is flowing, so there will be energy stored over that, and that is the half Li square. L is the inductance of the coil and I is the current to the coil. So this application this apply to any coil, but in practice only coils made of superconducting materials are sustained to store this kind of energy. Okay, so superconducting material coils made with superconducting materials can sustain currents high enough to provide the useful energy storage capacity. Okay, so SMES, basically SMES is differed from the ordinary coil because it is made of the superconducting material. So SMES coil needs to be cooled to a temperature below the critical temperature. For superconducting material, a critical temperature is defined. So when we use the SMES for the energy storage, we will have to provide a cooling system so that the temperature of that SMES system should not go beyond the critical temperature, otherwise that will be disrupted. So SMES coil needs to a temperature below the critical temperature of the superconducting material used to make the wire. The critical temperature depends on the type of the material. Okay, so low temperature superconductors, that is LTSCS, are either basic metallic elements or alloys, and they are having the critical temperature of 20 K. Okay, that is minus 253 degrees Celsius. Or high temperature superconductors are complex ceramics with critical temperature of 133 Kelvin. Okay, so better is to use the high temperature superconductor, those are the complex ceramics. Okay, so this is the diagram of the EDLC and SMES. Okay, so here this is the metallic electrodes. Okay, this orange color, this is the metallic electrodes, this is the porous carbon. Okay, and this is the porous carbon. Okay, and these are the porous carbon. Okay, and this is the polymer. Okay, membrane. Okay, so this is the diagram for the SMES. This is the SMES coil. Okay, here converters will be there that will convert the energy. Okay, from AC to DC. This is the notation for the AC, this is for the DC. So converter will be there for converting form of the energy from AC to DC, and this coil will be charged. So now we will go through the basic formula. So if how these are working, let's suppose two charges are there, Q1 and Q2, those are separated by a distance R12. So there, suppose like charges are there, so they will repel, and opposite charges will be there that will attract. This is the Coulomb's law. So there will be the force, electromagnetic force. So half and this force can be defined as 1 by 4 pi epsilon Q1 Q2 by R12 square, and this is for the making it vector quantity. Okay, so 1 by 4 pi epsilon is having the value 9 into 10 to the power 9 Newton meter square per Coulomb square. So electric charge produces electric field. Okay, so suppose at any point charge q is there, so it will produce an electric field of 1 by 4 pi epsilon q by r square. Okay, so electric field will exert a force. Okay, that force is q into E. Okay, so this force is also known as the electric stress. Okay, so electric energy and potential, we can define that also. So what is the electric work done against any electric field is stored as the electrostatic potential energy. So okay, so this is the potential. Okay, so V is the electrostatic potential, that is the electrostatic potential energy, that is work done against an electric field to store a charge. Suppose this charge is there, okay, and we are moving this charge from A to B. Okay, so we will have to do some work, we will have to provide some external energy. So if we are going against this electric field, okay, so then moving a 1 coulomb charge from point A to point B, okay, work done in that is known as the potential, 1 volt potential. So work done per unit charge is the electrostatic potential or voltage. So unit of potential or R energy per unit charge or joule per coulomb. So 1 volt is 1 joule per coulomb, and formula for this is the 1 by 4 pi epsilon q by r, and formula for electric field is 1 by 4 pi epsilon q by r square. So okay, so electric field is a vector quantity, the voltage is a scalar quantity. So now when we will transmit, as we have seen that we can store electromagnetic energy in two devices like EDLC and SMES, and as we store energy, okay, we can transmit that also over a wide range. Okay, so while transmitting energy from one place to other place, there will be some losses. Okay, so that losses is there due to the resistive property of the conductor. Okay, so electric current passing through a resistance will generate a heat also. Okay, so that's why we had seen that. So we will have to provide the cooling system also. Okay, so in case of capacitors, internal resistance is low, there is no cooling problem, there is no heating problem. Okay, so resistive energy loss in the transmission of electric power is a major problem over the long distance. Okay, as we know, R is proportional to R equal to rho L by A, R equal to rho L by A. As this will increase, resistance will increase, and loss, that is I square R, will increase. So resistance converts electrical energy into heat, that is nearly 100% efficiency, but this is not the complete story. Okay, so resistors power properties are there when there is current and voltage. Current and voltage in resistor can be related through this Ohm's law. Okay, so power, we can write power as V del V equal to V into del Q. Okay, so that is the power in a resistor, that is it is ability to carry a charge del Q, okay, through a voltage V. Okay, so P equal to dW by dt, dW is V into del Q, so we can write V into dQ by dt, that is V into dQ by dt is I, so we can write V into I, and we can write V as I into R also. Okay, so that is P is I square R. Okay, in case of transmission line, we write loss as I square R, not V into I. Okay, because this is the formula. So now power dissipated in a resistor, if there is constant V and I, suppose V and I are DC quantity, so we can write P equal to V into I, that is I square R. Okay, so when power is oscillatory, okay, that means AC quantity is there, voltage can be written as V naught Vt equal to V naught cos t. So It is Vt by R, that is V naught by R cos into omega t. So V naught by R, we had written this as I naught. Okay, so power is, if we multiply these two, so V naught I naught cos square omega t. Okay, so now if we average this, this is the formula when we are writing in terms of peak values. Okay, V naught I naught cos square omega t. So when we take the average, we will be having V naught square by 2R. Okay, so now power lines are used for transmitting the electromagnetic energy from one place to other place. Okay, so other form of energy are also being transmitted around us, like oils and gases are being transmitted from one place to other place through the tankers and pipelines. Coal and nuclear energies are also there. Okay, so coals are being transmitted over the trains, okay, through the transportation mode. Okay, so but wind energy, solar energy, hydro energy, tidal energy, how we transmit energy harnessed from that? What we do, we harness energy from wind, from solar, from hydro energy, or even tidal energy. These are harnessed first in the form of electrical energy, and then we transmit that through the long range, long distance. Okay, so in the process there are losses. When we convert wind, solar or hydro, see, when there is conversion of energy from one form to another form, there will be losses. Okay, so when first we are converting wind, solar, etc. to the electricity, we are having the losses, that is the conversion losses. Then electricity is being transmitted over the transmission lines to the substation nearest to the load centers. So in transmission segment also there will be losses. Okay, and from substation to the end users, in between substation to the end user, there is conversion. Okay, so these are the high voltage lines. Okay, so suppose 11 kV line is there. So for domestic use we are using 230 volt. Okay, for industrial use or for some commercial use, okay, we will be having 400 volt supply. Okay, so from 11 kV to the low voltage 230 or 400 volt, this conversion is also there at the end. Okay, so in that end segment also there is losses. So it is essential to know the percentage of losses. Okay, so because if we are transmitting energy, if we are generating energy from renewable or from other sources, we are generating power, we are generating electrical energy. So at that point also there is loss. During transmission there is loss. During distribution of power from substation to end user, there is loss. So the loss, how much loss is associated with this conversion, so we should go for that. So this is the cable through which we transmit power. Okay, so from this analysis we can say that choice is that aluminum often with steel support can be preferred. Okay, so this is the comparison of the conductor material for transmitting the power, electrical power. Okay, so transforming to electrical energy from one form to another form is also over the transmission line. Okay, so long range transmission line are there. Okay, so and we know mechanical energy can be converted into the electromagnetic transmission, electrical energy. So and again it can be converted back into the electrical energy. Okay, so all are based on Faraday's law of electromagnetic induction, because we studied that transformer is also based on the Faraday law of electromagnetic induction. So these are the some of the formula that you can remember it for your knowledge, and that these are the basic formula that you are studying from your schools, that are being used in the real applications. Okay, so these are some of the important formula that has been provided here in the slide. Okay, so when we go for the AC, there are 3 phases. Okay, so 3 phases are there for the transmission. So as we know, when capacitive load is there, current will be leading. When inductive load is there, current will be lagging. These all these things that you had studied in your first year subject. So this is all about the discussion about the electromagnetic energy. So these are the application areas of the EDLC. So a combination of battery and EDLC are being used. Okay, so you can go through this. These are the these things are already discussed. Okay, while we were discussing EDLC and SMES. Okay, so these are the application area. Okay, so but as we know, end of discussion is that since SMES system will need a cooling system also, but in parallel with EDLC we can use battery also. Okay, so that's why in most of the places EDLC and battery are being used, but importance of SMES is also there. Okay, so because this gives the instant voltage. Okay, in short span of time, if you need the power that in that SMES is being preferred. So this is all about the today's discussion. Thank you. Thank you.